I'd like to introduce to you Professor Renee James, who's an astronomer at Sam Houston State University. She's going to be the guest lecturer for this topic, so I'll hand over to her now.
So today we're going to talk about Kepler's laws. Now, Kepler was a mathematician living in the late 1500s, and he used the observations of the most amazing naked eye observer on planet Earth, and his name was Tycho Brahe. And Kepler took these observations and put them together to understand what the planets were doing. And the first thing that he wanted to test was what the planet orbit shapes were. Because everybody up until this point in history had assumed the orbital shapes were perfect circles. But unfortunately, if you assumed these were perfect circles, you could never actually get the predictions right. You couldn't figure out where Mars was supposed to be. You couldn't figure out where Jupiter was supposed to be. So Kepler understood that this was not the right answer. So he took Tycho Brahe's observations and then he did some calculations with them. And the first thing that he showed was that the orbits are not perfect circles, but they are a shape that we understood mathematically. And that's something called an ellipse. Now, an ellipse is kind of like a flattened circle, but a circle is an ellipse, kind of like a square is also a rectangle. And within this ellipse, you have a couple of focus points. And the sun is one of those focus points. And if you draw a line between the focus points and extend it out to the edges of the ellipse, you have a long axis of your ellipse, and that's something called the major axis. So when you look at the ellipse and you look at the major axis, mathematically we note that as 2a. So half of that major axis, something that's called the semi-major axis, is a.
So here we've got a generic ellipse. And the sun, as Kepler pointed out, is at one of the focus points. But there's another focus point because ellipses are symmetric. Now, each ellipse has sort of a long axis to it and a short axis to it, and the long axis is called the major axis. Half of that is called the semi-major axis because that means half major axis. Right now I've got it set up so that the semi-major axis is the same as Earth's. It's one astronomical unit.
And the flatness of your ellipse, how much it differs from being a perfect circle, is something that's called the eccentricity. And the flatter your ellipse is, the farther apart your focus points are, the more that eccentricity deviates from zero. Perfect circle has an eccentricity of 0. An incredibly flat ellipse would have something with an eccentricity more like 1.
So here's a little simulation where you can visualize the eccentricity. Right now, what we have is a planet that is in a perfectly circular orbit. And the eccentricity over here you'll see is 0. Now right now it's set with a semi-major axis of 1, which happens to be Earth's semi-major axis, because as far as Kepler knew, this whole thing was just a big scale model. He had no idea what the actual distances were. But you'll notice if you start increasing the eccentricity, the orbital shape gets flatter and flatter and flatter. You can see where the other focus point would be, but the sun is always at one of the focus points. So here is an ellipse that has the same semi-major axis as Earth's orbit, but a much greater eccentricity. You can see how much not like Earth's orbit it is here. This third red concentric orbit here is Earth's. Here's an ellipse that has exactly the same semi-major axis, but a very different eccentricity. And if you want to set it to Earth, you can. And if you want to see how much Earth deviates from being a perfect circle, you can do that too. So here's Earth's orbit in red and our hypothetical 0 eccentricity orbit in white, and you'll see that they're very, very close to being exactly the same, but not exactly the same, which is why it took somebody with the genius of Kepler to figure out what shape this really was.